Hello chemists, welcome to lecture 46. Let's first review transmutation. Transmutation is a process where atoms of one or more elements change into atoms of another element due to changes in the number of protons. Sometimes the number of neutrons can also change as well as mass number, but mainly transmutation changing in identity is mainly due to the number of protons changing. Now in today's lesson we'll focus on four types of nuclear reactions, which are natural transmutation, artificial transmutation, nuclear fusion, and nuclear fission. So let's first discuss our first type of nuclear reaction, natural transmutation. Natural transmutation is the transformation of the nucleus of one element into the nucleus of another element because the number of protons changes without the presence of another entity. And other names for natural transmutation are some things you've heard of already: spontaneous radioactive decay and spontaneous transmutation. And as the name suggests, natural transmutations can be identified on the basis that they always will only have one reactant that forms a different element or elements in the products. For example, Au-198 here with the mass number of 198 and atomic number or charge 79 will decay spontaneously or undergo natural transmutation on its own to emit a beta particle here in the products with mass 0 and charge -1. In beta decay, as well as the nucleus of a new element that's formed, which is Hg180, with a mass number 198 and atomic number or charge of 80. And this is natural transmutation because you have only one reactant or one nucleus in the reactant, Au-198, changing into another element on the product side. And natural transmutation mainly occurs in unstable nuclei with atomic numbers greater than 83, so they basically decay on their own. The way you can think about natural transmutation is that natural transmutation has one reactant always, aka an unstable nuclide that's heavy, decaying on its own because it's unstable in some way to form a new element. All right, so alpha, beta, gamma, and positron decay are all examples of natural transmutation. Next up is artificial transmutation, and artificial transmutation is the bombardment or hitting of a nucleus with high energy particles to bring about nuclear decay, and that results in a change in the element's identity because the number of protons changes. Artificial transmutations can be identified on the basis that they always have two or more reactants that form a different element or elements in the products. For example, Al27, with mass number 27 and charge or atomic number 13, is bombarded with this high energy alpha particle here, also known as He4 with mass number 4 and charge or atomic number 2, to form phosphorus 30 here on the product side with mass number 30 and atomic number 15, and a neutron with the mass number of 1 and a charge of 0. And this is artificial transmutation because there are two reactants or two nuclides in the reactants, Al27 and He4, changing into a different element on the product side, P30 here. And artificial transmutation usually occurs in stable nuclides that require high energy particles to bombard or hit them and start the reaction to change their identities. So basically they don't happen on their own, they need to be bombarded with a high energy particle for them to start. The way you can think about artificial transmutation is artificial transmutation has two reactants, usually a nuclide and a high energy particle in the form of radiation, reacting to form a new nuclide or new nuclides, plural, sometimes with the release of additional particles such as a neutron here in this example. We'll discuss more how artificial transmutation can be distinguished from the next two nuclear reactions, fission and fusion, very soon. All right, so next is nuclear fission. Nuclear fission is a splitting of one heavier nucleus, called a parent nucleus, into two or more smaller nuclei, called daughter nuclei, because the nucleus is bombarded with subatomic particles, and usually this is in the form of neutrons. Also released in the products is usually energy as well. All right, now by smaller nuclei in this definition, I mean smaller in the sense of nuclei with smaller masses than the original. It's also worth noting that common examples of heavy nuclei that you start with and that you bombard with neutrons are either plutonium or uranium. So look out for those as hints of possible nuclear fission. Now, an example of nuclear fission is one heavy nucleus, U-235 with mass number 235 and atomic number 92, being bombarded or hit with the neutron here in the reactants to split into two smaller nuclei, Ba141 with mass number 141 and atomic number 56, as well as Kr92 with mass number 92 and atomic number 36, as well as three neutrons and energy. So these two lighter nuclei, Ba141 and Kr92, are lighter because they have masses less than that of the original nuclide's mass of 235. All right, so fission is also shown in a diagram here with one heavy nucleus, U-235, being hit with this neutron up here. So you're hitting a heavy nuclide and splitting it into these two smaller nuclei, SR94 with mass number 94 and atomic number 38, and XE140 with mass number 140 and atomic number 54. Okay, and you also have, in addition to this, the release of two neutrons as well in the products. Now, SR94 and XE140 are lighter because the masses 94 and 140 are less than the original 235 from the heavier nucleus U-235. All right, so that's fission in a nutshell. Next is nuclear fusion. So nuclear fusion is a joining of two smaller nuclei to produce a larger nucleus, along with the release of energy in most cases. So make sure you take note of that and add that to your notes. Obviously, by larger, I mean that the nucleus in the products that forms has a greater mass than either the original two smaller nuclei did usually. And it's also worth noting that common examples of smaller nuclei that you join to form a larger nucleus are hydrogen and helium, so look out for those as possible hints of fusion. Now, an example of nuclear fusion is shown here, where these two lighter nuclei, H3 with mass number 3, atomic number 1, and H2, mass number 2, atomic number 1, combine together to form a heavier nucleus, He4, in the products here with mass number 4 and atomic number 2, as well as the release of a neutron and energy in the products. And the heavy nucleus, He4, is heavier because it has a mass greater than that of either of the original nuclide's masses. And fusion is also shown here in a diagram with these two lighter nuclei, H2 and H3, combining to form one heavier nucleus, He4, along with the release of a neutron and lots of energy. And actually, this is just a diagram of the example I showed here, so it kind of just visualizes this really nicely. All right, let's now discuss why nuclear reactions produce so much energy in the first place. We learned in the last unit, if you remember, that nuclear reactions release more energy or produce more energy than almost any other chemical reaction. Why is this? Well, the answer is something to do with a phenomenon known as mass defect, where the mass of individual protons and neutrons making up the nucleus of an atom is greater than the total mass of the nucleus itself. All right, so we'll see why mass defect occurs in a minute. I wanted to go first, however, over the relative masses of protons, neutrons, and electrons in AMU in a more exact way. Protons have a relative mass of 1.00728 AMU. Electrons have a relative mass of 0.000549 AMU, and neutrons have a relative mass of 1.00867 AMU. And this will come in handy soon. All right, let's explore the mass defect of carbon-12 now. Carbon-12 has 6 protons, 6 neutrons, and 6 electrons if you calculate it. And if we multiply the mass of each of these subatomic particles, relatively speaking to one another, by the number of subatomic particles in carbon for protons, neutrons, and electrons, we get mass of protons for carbon-12 is 6 times 1.00728 AMU, which equals 6.04368 AMU. The mass of neutrons in carbon-12 equals 6 times 1.00876 AMU equals 6.05256 AMU. And the mass of electrons equals 6 times 0.000549 AMU, which equals 0.00329 AMU. And the total mass combined of all three of these, for all three of these particles, is 12.09953 AMU for the mass of the particles. But you'll find out, however, that the mass of the carbon-12 nucleus is less than this one is, because it's only 12 AMU. All right? In other words, if you think about this, the mass of the products you end up with, in other words, a carbon-12 nucleus, is actually less than the mass of the reactants, aka the individual subatomic particles that make up carbon-12. So the mass of the products, which is the nucleus, is less than the mass of the reactants, which are the mass of all the particles combined together. Why? Well, what happened to the missing mass here was that the missing mass converted to energy, related through E is equal to mc squared, this famous equation made famous by Einstein, where mass is multiplied by the speed of light squared to get energy. That is to say that, in other words, nuclear reactions like transmutations, fission, and fusion produce way more energy than other reactions do, because a small amount of mass converts to a large amount of energy just based on this equation right here. C is 3 times 10 to the 8th, and if you square that and multiply by that mass, that small amount of mass can just convert to tons of energy. All right? Which is what we saw with fission and fusion in the products, for example, in the previous slides. You should also know that transmutations, fission, and fusion all involve inelastic collisions, where some kinetic energy actually is lost because it's changing to other types of energy, even though momentum is conserved. And recall also for part of the homework that this also happens with real gases. So make sure you take note of that. Okay? So last, let's discuss how you can identify nuclear reactions very easily. Natural transmutations can be identified by the fact that there's only one reactant that undergoes spontaneous radioactive decay. Artificial transmutations are identified based on two indicators, which is first of all that there are two reactants that form a new element or elements, with one reactant being much heavier than the other in mass. Okay, and fusion is identified by three indicators. First off, that two lighter nuclei combine to form a heavier one. Secondly, the lighter nuclei are usually hydrogen or helium. And third and finally, both nuclides in the reactants are around the same mass, or they have around the same mass number. All right, fission is identified by three indicators as well. First off, by the fact that one heavy nucleus splits into two lighter nuclei. Also, the fact that the heavier nucleus in the reactants that you start with alone is usually uranium or plutonium that you hit with a neutron. And also, speaking of which, the third indicator is that neutrons are either being absorbed in the reactants, being released in the products, or both in most cases. So take note of those, okay? Finally, I'd really like to quickly go over these review questions. This is just to explain it. This is already listed on your homework, so if you choose not to listen to this part, you can totally skip it if you'd like. Just make sure you add these parts to your notes before you move on. But if you do need an explanation, here it is. So number one are terms you should know, so I'm not going to go over that. Number two, recall that in all nuclear reactions, a small amount of mass converts to a large amount of energy. Number three, the four nuclear reactions are natural transmutation, artificial transmutation, nuclear fission, and nuclear fission. Sorry, fusion, my bad. Number four, nuclear reactions make more energy than others do because a small amount of mass changes into a large amount of energy. Remember, E is equal to mc squared. Number five, one advantage of fusion over fission that I didn't go over that you should know is that nuclear fusion generally produces more energy than nuclear fission does. Number six, if you look at this reaction, the sum of the masses is slightly less than the sum of the products. Sorry, the sum of the products is slightly less than the sum of the reactants because some mass changes into a large amount of energy. Number seven, three instances in which inelastic collisions occur are nuclear reactions like fission and fusion, and real gases, because in all three of those cases, some kinetic energy is lost. All right, number eight, just compare atomic masses in the top left and atomic numbers in the bottom left and subtract to compare the number of neutrons. And when you do that on your own, you'll find that the atomic masses, the number of protons and the number of neutrons are greater for nuclear fission than for fusion. And recall that fusion joins lighter nuclei to form a heavier one, while fission splits a heavy nucleus to form two lighter nuclei. All right, last number nine, the first equation here is artificial transmutation because the reactant mass of Mg24 is much larger than Li7. Also, you have two reactants, and finally, the most obvious sign is that you have two nuclides on both sides, Mg24 and Li7 in the reactants and Si30 and H1 in the products. So this cannot be fission or fusion because remember, fusion is two lighter to one heavier, and fission is one lighter to two heavier. But in this case, since you have two on both sides, it can be neither one of those. So the only option you have is since you have two reactants here, you know it's obviously just going to be artificial transmutation in general. All right, please add this last indicator to your notes for the first equation. All right, the second equation is fusion because two reactants very similar in mass that are lighter combine to form one nucleus, 2,2-He, and also in addition to that, you also see that neutrons are released. Okay? The third is fission because one heavy nucleus, U-235, captures a neutron in the reactants, and in the products it splits into two lighter nuclei, Xe-133 and Sr-100, along with the release of three neutrons. So you know that's obviously going to be fission. The last equation is artificial transmutation because the reactant masses are very different. In addition to that, if you build up more on that, you also have two reactants. And finally, what makes this not fission but rather artificial transmutation is that only one nuclide is produced instead of two lighter. So since only one nuclide is produced instead of two lighter, this cannot be fission because if you start with a heavier nucleus, you need to go to two lighter if you want it to be fission. But since you're only producing one lighter nuclide, this cannot be fission. So as a result, this is just artificial transmutation because it doesn't match the definition of fission. So please add this last indicator to your notes for the last equation. All right, that's it for tonight's homework. Make sure you do the questions. See you tomorrow. Bye-bye.